We've been looking at the idea of integration to find areas under curves and find the integrals. Well, it's terrific if we know how to integrate the function. But there are some functions that we don't know how to integrate. And there are others that are difficult to integrate. So sometimes an approximation is an easier way to go, or a quicker way to go anyway. Now you remember when we did the rectangles, it only took us to 10 rectangles and we were pretty close. Yeah, so it just depends on the number you have to how accurate you want it. To do the outer rectangles and the inner rectangles every single time, and then averaging it, there's a quicker way, and that's to use a trapezium. Because if you think about our rectangle, if we were to join the two corners of the inner and the outer, we'd get a trapezium. So effectively, here's the area we want to find here. What I'm saying is if we join those two corners, it's like joining the corner of the inner rectangle to the corner of the outer rectangle. It's going to give us a better approximation than just a rectangle. So if I used 1, then I'd say, well, height, which is b minus a over 2, whatever that function value is, plus whatever the other one is. 1's usually not a great one, but just like we saw with the rectangles, the more we have, the better the estimate. So if I did it with 2 trapeziums, or trapezoids, let's split it into 2, and you can see, well, already the gap's going down pretty quickly there. So c minus a on 2, b minus c on 2, but because I put c right in the middle, they're going to be the same. So I could factorise that. I just chose the c minus a on 2. I could have just easily had the b minus c on 2. And we'd end up with function a plus twice function c plus function b. Okay. Now if I split it into 3, again I'll make them equally spaced. There's the 3, but once again c minus a on 2 would be the same as d minus c on 2, would be the same as b minus d on 2. So I could factorise that out. So every single time I'm doing this, I end up with the same sort of pattern. I'm getting 1 times the function value at the end, the actual function values that we're integrating between, but twice all the ones in the middle. So all right, that's going to be our formula. So we know the exact area is the integral. We can approximate it with h on 2, so the height of whatever our trapeziums end up being. I start the first one at y0. So I call the first one y0, the last one yn, and then it'll be 2 times the others. It's a very technical formula. 2 times the others. Now the reason I start with 0 is so that n always ends up being the number of trapeziums. You'll see some books start with 1, but they'll end at n plus 1. So for mine, n's the number of trapeziums, and h could be calculated by b minus a divided by the number of trapeziums that we have. So keep in mind, there's always going to end up being one more function value than there are trapeziums. Because we start at 0, we end at n, so we end up with n plus 1 function values. Of course, you don't only have to use this for area. It could just be for approximating an integral. Still the same idea. It's just finding a number instead of an area. I've picked one that we know the area exactly for, although at this stage we don't actually know how to integrate. Because of course 4 minus x squared to the power of a half, square root of 4 minus x squared. Yeah, we're talking about a semicircle. Well, actually we're talking about a quarter of a circle because I'm going from 0 to 2. So we can see how good our estimate's going to be. Okay, height will be 0.5 for this one because we've said 4 intervals. Sometimes they say intervals, sometimes they say sub-intervals, sometimes they call them strips, and sometimes they call them trapeziums. There's my table of values that are filled in. Now, there's my formula, y0, 2y others, yn. So I don't get confused as to which ones to multiply, above my table of values, I like to remind myself, okay, the end ones I'm multiplying by 1, and all the ones in the middle I'm multiplying by 2. Maybe it'd make more sense to put it underneath, because it's actually the y values I'm multiplying, but anyway, let's sub in. So 0.5 on 2, subbing those numbers in. Notice I did them to 4 decimal places, because the questions asked for 3. So I figure if I carry one extra decimal place, that'll account for any rounding error. And then I'll just round to the third decimal place at the end, and I get 2.996. So how good was it? Well, exact value is pi, because I deliberately chose that one. So a quarter of the radius squared becomes one. So percentage error, actual value minus our approximate, times by 100, out by 4.6%. Obviously, if I did more trapeziums, the better it would get. Well, there is another rule. You see, it seems a bit strange to estimate the area under a curve with a straight line. It makes more sense to estimate the area under a curve with a curve. And Simpson's rule uses parabolas. And in fact, if the function you're using Simpson's rule for is either a quadratic or a cubic, it'll be exact. It'll work out the exact value. That's not that big a deal because, of course, it's not that hard to integrate quadratics or cubics there. All right, so area, what's the difference? The difference is in the middle. Instead of multiplying them all by 2, the odd ones, and when I say the odd ones, I mean y1, y3, y5, y7, not the ones that have odd numbers in them, I multiply by 4. And the even ones, I multiply by 2. Oh, and it's h over 3, not h over 2. So let's do the same question. There's my table of values. So the end ones I will multiply by 1. Then basically it alternates, 4, 2, 4. To get a great approximation, you want that to be symmetric. So you wouldn't want an additional function value, because in the middle then it would go 4, 2, 4, 2, and you lose that symmetry. So it seems to work better when we have a nice symmetric 1, 4, 2, 4, 1, that sort of thing. Okay, let's sub in, and we end up with 3.084 for this one. So a lot closer to pi. How much closer? Well, that one's only out by 1.8%. There is an alternative way of writing out the setting out that I saw in a solution once and looked at it and went, what the heck's going on here? So I sat down and I went, all right, let's try and prove it. And I did prove that it works all the time, so that was good. It was for trapezoidal rule. And I thought, well, sure, if it works for trapezoidal rule, it'll work for Simpson's rule as well. So I tested that one, and that worked as well. Here it is, that our question with the trapezoidal rule, there's our answer. So basically on the top is still that the end ones 2 times all the middle. But on the bottom of the fraction, you're just writing that pattern. 1 plus 2 plus 2 plus 2 plus 1. And you multiply it by the total width of the area you're trying to find. So b minus a. In this case, 2 minus 0. And it works. Comes up beautifully. 2.996. And then the Simpson's rule one, I'd do the same thing. So there was our table of values. Sub in, so that's what we would have done. 2 times that, 4 times that, and so on. But on the bottom, we write down the pattern. 1 plus 4 plus 2 plus 4 plus 1, multiplied by the 2 minus 0. And it works. So 11I and 11J. One's on trapezoidal, one's on Simpson's.